Okay, so there are some corrections which I have not yet done. Remember, Kostu was talking about this would be better written as delta K0. I'll do that. I, in fact, haven't gotten enough time to prepare notes today. So anyway, coming back to what we were doing last time, was we converted the Hamiltonian into the the momentum space creation annihilation operators, which were called C2 and C3, and uh, and we found that the entire expression, which involves psi 2m at times psi 3m plus 1 and psi 2m and psi 3m, these two pieces, if you put them together, then you can write down the Hamiltonian in an off-diagonal form like this. Okay, and of course, this matrix can be diagonalized. That diagonalization would require us to write down a new set of operators, which are linear combinations of C2 and C3. And with respect to those creation annihilation operators, this Hamiltonian would be diagonal. Okay. Now, of course, it's kind of easy to diagonalize this 2 by 2 matrix, and the eigenvalues are given by E plus minus, which are just opposite of each other, plus minus times square root of sine squared k plus cos k minus lambda whole square. Okay, and and we also checked, we plotted these energy eigenvalues for lambda greater than 1, where you have a gap and the spectrum is symmetric. We would use this fact later, and when lambda is equal to 0, then there is no gap. Okay, so for k equals 0, the energy is exactly equal to 0. Okay, and so we are really interested in exploiting this behavior around lambda equals 1, that around lambda equals 1, the gap opens up in the spectrum. Okay, and that is some kind of non-analytic behavior of the spectrum, and we want to ask what happens to the system when lambda is close to 1. Okay, fine. So of course, Hamiltonian would be diagonal not in the C2 C3 basis. So what we do is we'll denote the new basis as D plus and D minus, in which the Hamiltonian is diagonal. D plus are the annihilation operators, and D plus dagger would be creation operators for energy E to be E plus, which is just plus, E plus is just Ek, whereas D minus are annihilation operators and D minus dagger are creation operators for the states with negative energy, where the energy is minus Ek. And therefore the Hamiltonian is actually Ek D plus dagger D plus minus D minus dagger D minus. Okay, so that is the kind of form the Hamiltonian has. Okay, now I'm not telling you what is the linear combination of C2 C3 that gives you D plus and D minus, but that is not a very difficult thing to do. All you have to do is to find out which matrix, similarity transformation matrix, diagonalizes this. That would tell you how you write down this column vector in terms of D plus and D minus. Okay, for 2 by 2 matrix, it's not such a complicated exercise. Okay, fine. So of course, this is the description in terms of Majorana fermion and the diagonalized Hamiltonian with respect to a new basis of creation annihilation operators. But the ground state of this Hamiltonian would correspond to filling up all negative energy states. Now remember, the negative energy states in this particular problem, if you go back, you will realize that this integral was done from k equals 0 to pi. Okay, so it's not like, unlike the Dirac equation case, where when you try to fill up the negative energy states, you are filling up from minus infinity to 0. Okay, this is not the situation here. Here what we are doing is we are integrating over k from 0 to pi, but fill up states where the energy is minus Ek. Okay, So that is what we mean by ground state being a state with all negative energy states for a field. Okay, so that is what we want to do. Okay, so let's kind of go back to the transformative formalism just to understand as to what is it that we are trying to do by filling up this kind of states. Okay, so now remember that in the transformative formalism, we basically said that when you take thermodynamic limit, what really matters is the hello. Can you hear me?
Yeah.
Yes,
Oh,
sir.
okay.
But your voice is crackling.
Yeah, because it says it is the connection is unstable, so that's why I immediately asked. Well, it is on the phone, and yes. Hello.
Nothing, sir. Nothing. Continue,
Oh,
sir.
okay. Yeah. So, and well, institute network is down anyway, so I have to. I'm at the mercy of my telephone connection. If that also goes bad, then very little can be done. But let's hope it works. Let me keep it closer to the window or something. Hopefully the signal is better there. Oops. Just give me a second. Okay, is it working? Hello?
Yes, sir. Yeah. Yeah, yes.
Okay, okay, okay. Yeah. So, okay. So now, so as I said, let's get back to the transformative formalism. And in this formalism, what we were interested in was to look for the largest eigenvalue of the transfer matrix. Okay. Uh, so, which kind of sounds opposite of what we are trying to do in the Hamiltonian formalism, because in the Hamiltonian formulation, we are looking for ground state of the Hamiltonian. Okay. But that is not a contradiction, because what happens is that, like, that in case of the relation between the transfer matrix and the Hamiltonian is like this, that transfer matrix T is exponential of minus beta h. So therefore, to get the largest value of the transfer matrix would require the smallest eigenvalue of h in the problem. So any eigenvalue which is higher excited state of the Hamiltonian, they would give you lower eigenvalues of transfer matrix because of this relation e to the minus beta h. Okay, so therefore, uh, looking for the largest eigenvalue of transfer matrix is equivalent to looking for the ground state of the Hamiltonian. Okay, so therefore, I just wanted to kind of get this connection cleared so that we know that we are doing the same stuff, so no matter which formalism we are looking at.
So
Okay.
would you go back a couple of slides?
Yes, yes, sure. Yeah.
Yeah,
Yes.
this. Okay, those D's are constructed some linear combination of C2 and C3.
C2 and C3. Yes.
Like, but we don't need to bother about what is it specifically.
Well, yeah, actually, in some sense, no, because we really are interested in behavior of the energy spectrum than the diagonalizing basis.
Okay.
But what I was saying was that, like, it's not difficult to find out what D plus D minuses are in terms of C2 and C3. You just sum 2 by 2 matrix multiplying them. Okay. But it is not important for our analysis. That's why I haven't given.
Yeah, all right. Yeah.
Okay. Fine. So coming back to this one, so this is something I just explained. So suppose, let's go back to the same notation that we used earlier for the transfer matrix. That suppose the eigenstate is given by alpha and the eigenvalue is T alpha. then the transfer matrix would be written as sum over all possible eigenstates with the corresponding eigenvalues, and the partition function, which was t to the n2, would be given by t to the t alpha to the n2 in this particular case. Remember, this is a row to row transfer matrix, and in the y direction we have n2 sides with periodic boundary conditions. So we are going to take a trace of t to the n2, and trace would take care of all these alpha guys, which are sitting at the end of the t to the n2 expression. And once you get rid of those, you basically get t alpha to the n2, because all these states are in a diagonal basis. Okay. Now suppose T0 is the largest eigenvalue among these, and then after that the next one is T1, next the one after that is T2. Suppose we order them in that particular fashion, or we label them in that particular fashion. Okay, then our partition function, we can just pull out T0 to the n2 outside, and the partition function would look like T0 to the n2 into 1 plus T1 by T0 to the n2 plus T2 by T0 to the n2 plus dot dot dot. Okay. Clearly, T1 by T0, T2 by T0 are quantities which are less than 1, because T0 is the largest eigenvalue. And if you go into if you take the thermodynamic limit, then these terms are highly suppressed. Okay, so in that sense, all lower eigenvalues of the transfer matrix, or all excited states of the Hamiltonian, has exponentially subleading contribution to the partition function when you are taking thermodynamic limit. Okay, and therefore it suffices to concentrate on the behavior of the ground state of the Hamiltonian, or behavior of the largest eigenvalue of the transfer matrix, which are both same things actually. Okay, so you look at this one. If you take the thermodynamic limit, then you can ignore remaining pieces and just concentrate on T0 to the N2, and then your free energy is going to look something like minus kBT times N2 times log of T0. Okay, so that's the free energy of the system. Okay, fine. So what we want to do is to compute the ground state energy of the system, and as I said, that involves the integral over k going from 0 to pi. Okay, and for arbitrary k, the energy was written as Ek is equal to square root of sine squared k plus lambda minus cos k whole squared. Okay, but remember that the ground state energy, as I said some time ago, that ground state energy corresponds to filling up all negative energy states. Okay, and as a result, E0 is actually minus Ek integral. Okay, for all k values. So that's why it's minus sign. Okay, so we are just trying to fill up all those states. Okay, so let's try to compute this quantity. Okay, now remember, going back to this graph. Okay, in this graph, as you can see, that nothing special happens for finite value of k. Okay, whatever happens really happens at k equals 0. So whether the spectrum is gapless or whether the spectrum develops a gap, okay, all that happens in the neighborhood of k equals 0, and clearly all that happens in the neighborhood of lambda equals 1. So what we want to do is actually find out how does this ground state behave in the neighborhood of k equals 0 when lambda is close to lambda equals 1. Okay, and how does this system develop gap, and what kind of non-analytic behavior the system exhibits in the neighborhood of lambda equals 1. Okay, so therefore although we are doing the integral from 0 to pi, okay, our real focus is going to be in the neighborhood of k equals 0. Okay, so this is what we will do. Okay, so to determine how the system develops this gap, okay, we will consider lambda to be 1 plus epsilon, where we take epsilon to be small. Okay, and then compute the Ek, which is this expression, the square root, okay, for lambda equals 1 plus epsilon. So that is just sine squared k plus 1 plus epsilon minus cos k, which is just substituting the value of lambda and whole squared. And now you can just expand this expression. So when you expand, you get a cos squared k. So you have a factor 1 coming from sine squared k plus cos squared k. There is another factor of 1 coming from the square of this quantity, which is sitting around here. Then there is a cross term 2 epsilon plus epsilon square piece sitting from square of this, and a cross term between 1 plus epsilon and cos k, which is sitting around here. Okay. So you can simplify this. These two terms plus this gives you 2. You have a 2 epsilon coming from here and epsilon square, and 2 times 1 plus epsilon. So you have 2 times 1 plus epsilon in front of two quantities, and the next quantity, which is non-vanishing, is of order epsilon square. So what we will do is we can pull square root of 2 times 1 plus epsilon out, and we can write down this expression as 1 minus cos k. Square root of 2 times 1 plus epsilon is pulled out, and then there is a term which is proportional to epsilon square, which is plus epsilon square upon 2 times 1 plus epsilon, okay, whole to the half. Okay, so that's how this expression is going to look like in the neighborhood of this quantity. Right now everything is exact actually, because we haven't done anything. We have just rearranged the expression. Okay, so this is what I was saying, that for small epsilon, from the graph we can see that the interesting behavior really happens near k equals 0. Okay, so what we will do is that we will try to compute the difference between the ground state energy when lambda is equal to 1 plus epsilon versus ground state energy when lambda is equal to 1. Okay, so that is the one which will tell us how the system is developing gap as lambda changes. Okay, any questions at this point?
So how are we going to interpret this difference?
How are we? That is the measure of the gap of this in the system, right?
I mean, lambda was k tilde by k, something like that.
That is right. Yeah.
And that was fixed when the crystal is given to us, right?
No.
I mean,
No. It's not. It's not like when you do experiments, no, you can do various things with the crystal, right? So, for example, you can put pressure in one direction that could change the coupling in some direction, and changing pressure can be done by various different ways. You can introduce some additional impurities in the system, which could kind of change the values of k and k prime. Non-magnetic impurity, like for example, you have some magnetic material and you kind of add calcium to that. Calcium is non-magnetic, but if it sits in the interstitial space, it can affect the couplings in x direction versus y direction. If you don't want to do that, you can explicitly put physical pressure on the system to change the values. So variety of things can be done even if you are given a crystal of a very specific kind actually. Okay. So in fact, these experiments are done by, tuning the k versus k prime in the system. No, not k prime, k tilde. Okay. So it is eminently possible. If you ask experimentalists, the experimentalists will tell you how many different ways one can actually manipulate these parameters.
I mean, in our problem, it was fine, but the original problem that we were studying was some XY crystal.
That's right.
And that we reduced to this X like linear model with some transverse field.
Yeah.
And while comparing this with the original problem, we had some approximation like k and k tilde are small.
Yes. So in fact, what will happen in this particular case, that lambda equals 1 corresponds to lambda in fact would be a measure of difference between T and TC. So lambda itself is going to be proportional to kind of T minus TC. in some sense, or rather epsilon, I should say. Okay. As we'll go ahead, we'll see that like the behavior of specific heat, for example, that we will compute, okay, is actually picked up from the behavior of free energy as a function of epsilon. Okay.
Oh, I thought we were just doing some sort of a Taylor expansion in epsilon and then we'll set it to 0 or something.
No. We want to figure out as how the system develops non-analytic behavior as epsilon starts getting smaller. Okay.
Okay.
So we don't want to set epsilon to 0 exactly. We want to keep epsilon small and ask how the system develops singular behavior. Okay. Remember, even in mean field theory, we determined the critical exponent when we said that T approaches Tc from above versus T approaches Tc from below, and those were some different parameters, gamma versus gamma prime, and stuff like that. So what we are doing here is we are approaching the critical temperature only from one side. Okay. Okay. So maybe let's get back to what we were doing. So here's the expression. So far we haven't done anything. Okay. But what we'll do now is to find out what is the difference between the system at lambda equals 1 plus epsilon versus lambda equals 1. So here's the expression. So, okay. So let me actually go back to this thing. So if you set epsilon equals 0, then of course you have a simple expression. This is square root 2 times 1 minus cos k to the half. Okay. So you get that expression. Okay. Minus the lambda equals 1 plus epsilon factor. Now it appears in the opposite order because we are actually summing negative energy states. Then both of them are negative sign, and that's why the sign factor is flipped here. Okay, but this is the expression. So now you can of course take 1 minus cos squared k to the half out and kind of expand this expression, or you could just kind of look at this expression in the neighborhood of k equals 0 because that is the most interesting part, and see how the system behaves. Okay, so what we'll do is we'll really look at do the second thing, namely look at the system in the neighborhood of k equals 0. Okay, so if you do that expansion, you get terms like this. Okay, so you have so remember, like cos k has a behavior which is like 1 minus k squared by 2, right? That is how it would behave in the neighborhood of k equals 0. So the term 1 would just cancel, and k squared by 2 is the one which will give you k upon square root 2 factor. Okay, from here. You can do something similar here, but in this particular case, k wouldn't come out because there's an epsilon sitting around, so you get an expression like that. Okay, so you need to do a little bit of manipulation to get this factor out this way, but this is how the expression would look like. Okay, fine. So now what we want to do is to look at the look at this particular expression. So this integral dk times k is kind of trivial integral. There's nothing to do. There's a second integral which is interesting, and that is the one we want to look at. I seem to have got a sign wrong. It should have been plus. I'm sorry. Okay, because there is a plus sign here. Okay, so it should have been plus actually. Okay. Bad. Okay, coming back to this, but that square root 2 cancels with the square root 2 here, and you get an expression which is like this. Okay, so you want to evaluate this quantity. Okay, so what we'll do is that we'll do evaluation of this by using integration by parts. So first term is this. Okay, so you take first element to be 1, second element to be the square root, and you get this expression. And then when you do it again, then you get dk times k into k upon square root of this quantity. Okay, so you can massage this expression again, because this is k squared upon square root of k squared plus epsilon squared. So you can write k squared as k squared plus epsilon squared minus epsilon squared and write down this expression in this particular form. Okay, fine. So you can again manipulate you can manipulate this expression again. Basically, you can take this integral to the left, because this integral is same as the integral on the left. Okay, so when you take it on the left, then you get left hand side to be twice the integral, because this has a minus sign. So you just take that factor out and you write down left hand side integral is equal to half times this piece plus this piece, because this minus sign and that minus sign. Okay, so that's how you get this expression. Okay, so all I have done is that I've used this middle term with a minus sign to be same as the left hand side. Okay, so when you take it on the other side, it just doubles. Okay, good. So first term is of course as it is. This quantity can be integrated, and you can check this integral that it is given by epsilon squared by 2 times log of k plus square root of k squared plus epsilon squared. Okay, so there are various different ways of writing it. There's a way of writing this in terms of tan inverse kind of quantity also. They are related to each other actually, these kind of transformations. Okay, but nevertheless, it is instructive to write that as a log, as we will see in a moment. Okay, fine. So now what we'll do is that we will take this expression and put it back into the difference of energies that we had computed. Okay, and remember that entire quantity was multiplied by square root of 1 plus epsilon. So we will multiply this expression by square root of 1 plus epsilon and multiply this by square root of 1 plus epsilon. Okay, so so what we get, maybe I can split screen to just yeah, here's the expression. So the first integral just gives you that k squared by 2 kind of factor. The second integral, which was the quantity that we have just computed here, okay, this should have been plus sign, I will correct that one, gives us the answer, which is this. So, but there is an overall minus sign here, so because of that, there is a minus k by 2 times square root of k squared plus epsilon squared times square root of 1 plus epsilon minus 1 square root of 1 plus epsilon times this piece. Okay, so that's the kind of behavior that we end up getting. Okay, now so in this case, like what you find is that like there are first two terms which are written out here have kind of relatively simple behavior as a function of epsilon. Okay, and that nothing very special happens when you try to take epsilon to be any specific value. Okay, whereas in the last term, the epsilon is sitting inside the logarithm also, and that is the one which is kind of responsible for generating some kind of non-analytic behavior. Okay, so what we will do is we will only concentrate on the non-analytic behavior of the system, and we will not worry about what happens to the analytic terms. Okay, so typically in the critical phenomena language, terms which are analytic are called non-universal, and in other words, it depends on which system you are looking at. The analytic terms would depend on how the Hamiltonian is defined, and it may be some set of quantities for say liquid gas phase transition, but it may be some other set of quantities for say Eigen model, or some third set of quantities if it was, say, binary alloy. But the non-analytic behavior is not like that. For all these three systems, since all of them belong to the Ising model universality class, the non-analytic behavior of the system for all three of them would be exactly same. Okay, and therefore, if you are trying to look for the universal characterization of certain critical phenomena, then it is better you focus on the non-analytic behavior of, say, free energy, okay, or various other quantities like various derivatives of free energy, than look at the analytic terms. Okay, so we'll therefore ignore the terms uh, which are analytic and concentrate only on the terms which are non-analytic. Okay, and the non-analytic behavior of the f would look something like epsilon squared times log of epsilon squared. Okay, that is the kind of behavior the system would have. Okay, so I should just check the correctness. Okay, so notice one thing, that like we are seeing this behavior because we are interested in looking at this energy difference in the neighborhood of k going to zero limit. Okay, so in that neighborhood, you can kind of see that k going to zero, this term would vanish and this term would kind of also vanish, and therefore the expression is really kind of depending on what is happening with log of epsilon. Okay, that is the kind of expression. Okay, so since there's epsilon square sitting outside, I wrote down the other term also to be log epsilon squared, and kind of added a factor of 2 in the denominator just to kind of get the same behavior. But you could write it in this form if you wish. Okay.
Would you go above again the
Yes.
expression? Would a little more?
Yeah, sure.
We are integrating over the entire region K, like even in
That's
the
it.
ultimate sense.
Yes. We are doing actually indefinite integral. We are not even plugged the values. We'll do that at the end of the calculation actually. So right now it's just an indefinite integral, right? Actual integral is from 0 to pi, but we are not doing that right now. Right?
And we are saying that this first term and the other term that we had, just the k term, they aren't important.
Yeah, because as k going to zero limit, this is kind of a well-behaved quantity. Even here, k going to zero limit would go as kind of positive integer power of epsilon. Okay, so nothing very interesting happens in this case. If you take epsilon going to zero inside square root of 1 plus epsilon, nothing happens. It just gives you 1, right? So this entire set of terms as a function of epsilon are analytic. Okay. On the other hand, here in the k going to zero limit, if epsilon goes to zero, then log of epsilon will diverge. Okay. So this divergent behavior, the singular behavior of the system, is what we want to pick up. Okay.
We are still taking k going to zero limit first.
Yes.
And how are we taking that exactly? Like just setting it to zero in this term?
Setting it to zero. Yeah. So that is why our expression is like this. Right? We have set k equals 0. Right? Otherwise, of course, there is a k dependence. But as you can see from the figure, nothing special happens for k non-zero. Okay. System develops, system has gap for all non-zero k's. System develops a kind of gapless behavior only at k equals 0.
Okay.
So that is where interesting stuff is happening actually. Okay. Fine. So what we'll do is basically compute the behavior, compute the derivatives of the free energy, and in the neighborhood of epsilon going to 0, and see what is happening to the system. Okay. So I think this is probably the last transparency today. So the derivative of f with epsilon gives you a term like that. Second derivative would give you a term which is like log of epsilon squared. Okay. So from this, we can actually read out the behavior of the specific heat, which goes as log of T minus Tc. If you treat epsilon to be a measure of how you approach criticality, okay, in terms of temperature. Okay. So now notice that the specific heat going as log of T minus Tc would tell us that the specific heat exponent alpha is 0. Okay, because this is going as log. Okay, but remember that in mean field theory also we got alpha equals 0. Okay, but the alpha equals 0 behavior in the mean field theory, if you can recall, was that it was just a discontinuity at across T equals Tc. That the specific heat had some value below T equals Tc and specific heat at some other value above T equals Tc, and they basically meet at T equals Tc with a gap. Okay. So simple discontinuity was the answer that you got in mean field theory. And because of that, we said that alpha was equal to 0. Whereas this alpha equals 0 is quite different because this specific heat is actually diverging at this point, right? Because log of T minus Tc would give you log of 0, and that is definitely singular. Okay. It's just that that singularity has does not carry any specific power as of T minus Tc. Okay, it goes as log. Okay, so I think this is all I wanted to say today. We could kind of pick it up from here next time. Sorry, today's lecture is a bit small.
CV was defined as del F by del E. I forgot the definition.
No. Second, specific heat is like a susceptibility, right? Temperature susceptibility. So you need to do a second variation of it. First variation is entropy, no?
Okay.
Right.
And we are setting epsilon as T minus Tc.
Epsilon is the measure of approach to critical temperature. Okay.
So we have done all this analysis in the neighborhood of those functions k and k tilde.
Yeah.
When they were approaching to 0.
That is right. Small values of k and k tilde.
That kind of meant that the coupling in y direction was infinite and coupling in x direction was very small.
Very small, yeah.
So will this all the results that we get here, will it be true for general two-dimensional eigen model?
Yes, in principle, you can show that these results would still be valid for general couplings. Yeah, so it is not immediately obvious from this analysis that you could do this, but like as you can see that we are looking at lambda equals 1. Lambda is actually a ratio of k with k tilde, right?
Yeah.
So k and k tilde both are going to 0, but they are going to 0 in such a way that k by k tilde is close to 1, right, in this analysis, right?
Yeah, but still, this is not the same behavior that we would see. I'm saying k tilde going to 0 is like coupling going to infinity in one direction.
That is right. Yeah.
So we cannot compare k and k tilde.
Yeah, that is right. So what we are doing is that we are trying to take k and k tilde as small, but that does not mean that we are really taking the limit of k and k tilde going to 0. What we are saying is that they are both small quantities, but the ratio is held fixed. Okay. So this is this kind of analysis. You don't have to do it in this particular way. We could have solved using this Onsager-like technique, where you can use some Kramer-Swanier type of duality to solve this problem, in which case you don't even have to make this anisotropic limit. Onsager solved it for arbitrary temperature and arbitrary coupling, in fact. Okay. It is just that showing Onsager solution would be kind of it may take probably about 7-8 lectures to go through all possible these things. So instead of doing that, I chose one particular example in which you can see how the system can be computed. But if you want to do, I mean, it's like there's a book by Barry McCoy and Wu, T.T. Wu, called Two-Dimensional Ising Model. It's like 600-page book trying to just solve two-dimensional Ising model in some various possible kind of limits. And of course, in spite of that, it is still a kind of subject of research. So what I'm trying to say is that, like, this is not the most general analysis of two-dimensional Ising model, that I admit. Okay, but this is one way in which you could kind of quickly analyze a system. You can see it's mapped to some fermionic system and stuff like that. There's some technique to be learned here. Okay, then saying that, like, we are actually doing an exhaustive job of understanding two-dimensional Ising model. Okay, we are not. To exhaustively study two-dimensional Ising model is a different integrable model course, actually, in some sense. So yeah, so I admit that, like, it's not most general, certainly.
Yeah, and one more thing.
Yes.
Epsilon is the ratio of k tilde and k. So, and k tilde and k were like a factor of beta times the coupling.
Yes.
So, like, the temperature has already been cancelled here.
Yeah, yeah. So.
Yeah. So why are we relating epsilon to?
Yeah, you'll have to probably wait for me to do Landau theory to understand this. Okay. So there are some residual factors which actually show up. So in Landau theory, there is a kind of better description of these as to why these are temperature dependent quantities.
Okay. Yeah.
Okay. So in the sense that, to put it a little differently, the couplings that one has written down initially in the model are some numbers. Okay, but effectively they themselves develop a temperature dependent behavior, and the epsilon actually picks up that behavior in some sense. Okay, so it is not immediately apparent here. I should have probably done Ising model after doing Landau theory. That would have given a little more coherent picture. But since we had solved 1D Ising model exactly, I thought I'll kind of back it up by 2D Ising model story.
What did you just say? Is this regarding why epsilon has temperature dependence?
Yeah, yeah. That, like, when you write down k upon k tilde, the naive beta dependence just drops out. Okay. So epsilon is kind of a difference variation of k over k tilde away from 1, right? So
like k tilde already has some beta dependence, right? Because it is exponential minus beta.
No, but even k had the same dependence. When you take k upon k tilde, the beta dependence clearly cancels out.
Oh, okay.
Okay. So it would appear that, like, epsilon should not have anything to do with the temperature. But that's not what happens. The system actually develops temperature dependence. So in Landau theory, for example, a mass term for the scalar field would develop temperature dependence. And so all critical behavior depends on how the mass changes sign, kind of stuff. We will see that, I think, soon. Okay. So I think I have only this much to say today. I'm sorry, it's a bit short lecture. Hello?
Yeah.
So if there are no questions, can we close the session today?
Yeah.
Okay, sir. Okay.
Okay.